pyramid. So very quickly, what we do is that we have two slits at a distance d apart. So this distance here is small letter d. And we have a screen, or in this case we use the whiteboard as a screen, but in general we talk about a screen where we can see the interference pattern. And we emit, or laser light is incident on these two openings, these two slits, so that we will get an interference pattern. So we will have light being incident on these two slits in plural. So this is laser light of a specific wavelength. And what do we detect on the screen? What did we get? Yep. Light. We got light.
Wow.
Was there a particular pattern in this light?
It was like lines, but like dotted,
Dotted lines?
kind of.
Yeah. What we got in the middle, right in the central here, we got bright light. We got red light because the laser was red. We draw it like that. And then we kind of see very closely, we see that we got light separated by distance. We got light here, and we got light here, and we got light here. And in between those regions with light, we got darkness or nothing. So we can either draw it in, usually we kind of draw it in black, even though it looked white because the whiteboard was white. So this one here in the middle, we got bright light. That was called the central maxima. It's denoted n equals 0. And then we had n equals 1 here, n equals 2 here, n equals 1 here, and n equals 2 here. Kind of how we labeled these maximas. So we basically got an interference pattern. Bright light in the middle, then you have dark fringes, followed by another bright light, and dark fringes, and bright light. That's what we refer to as the interference pattern. So bright light, that's a consequence of what? Why do we get bright light?
Constructive interference.
Yeah, constructive interference. So wave from this slit constructively interfere with light from this slit. And the dark one is due to destructive interference. Yeah. And we wrote down a formula saying that S is equal to the wavelength times the distance d divided by small letter. Do you remember what S is? What is S?
Is it the distance between each of the lines,
Yeah.
the lights?
The distance between two consecutive bright fringes. This is S, and this is S, and this is S. They lie pretty close together. So all of these can be found by using this formula. Lambda, what's that?
Wavelength.
The wavelength of the light. We see that the distance between the bright fringes depends on the wavelength. We saw that using red light, we got greater distances than we did for violet light because the wavelength of red light is bigger than the wavelength for purple light. Yep.
Just one question. So if the wavelength of the red light is bigger,
Yeah.
or greater than purple or violet,
Yep.
what makes it such that it has a greater distance between each constructor?
Yeah, that's actually a pretty good question. It's that difficult to answer, but we can kind of do it in terms of, if you go back to the ripple tank, right? Let's say you have a source here and you have a source here. If you kind of, so this is a source of wave here and this is a source of wave here, two sources of waves. So let's say I start with one specific wavelength. I can then draw this wavelength here, draw this wavelength here, and in another color I can draw the same wavelengths. And then you can kind of map out the regions where you get constructive interference. You get constructive interference in the middle. So if I were to answer your question, what makes these points come closer if the wavelength decreases is basically because I then would draw the diagram with smaller wavelengths. So these, in the ripple tank, when I increased the frequency, the pattern kind of came closer together. That's basically what happens here.
Oh, so there are more waves per second, and so it's smaller, and so you just get it.
Yeah.
Because
Yeah. So if you have let's say you have constructive interference in the middle here, and you have constructive interference here, and you have constructive interference here, and you kind of keep making that pattern. If you increase the frequency, reduce the wavelength, these patterns would just come a lot closer together, reducing the distance between the bright fringes here. Yep. So you can use that explanation for water waves for light as well. All right. But this formula here, it's important to realize that this formula is only true for de Young's double slit experiment, the double slit. If we remember that when I did the experiment with multiple slits, so let's say here's a diffraction grating, this can be seen as having multiple slits. Here you have 300 slits per millimeter. So that's a lot of slits. And the same thing happened. You remember I did an experiment, I put it from you. I just saw a pattern like this, but the distances was much further apart. Yeah. This deriving this formula here, this has a yep, thank you. Small angle approximation. It has, when I derive this formula here, I use a small angle approximation. I can do that for Young's double slit because these distances are very small. If I measure this angle here, I take the central line from the midpoint to the central maxima, and I take the line to the first maxima, almost, I get a theta. For Young's double slit, this theta will be very small. That will not be the case when I introduce 300 slits per millimeter, because this distance here will be very small. This distance here will be greater. The angle will become greater, and I can no longer use the small angle approximation. So we kind of need to learn how to do it without the small angle approximation. At the same time, we can, for instance, use the same equations that we're going to use now to calculate the wavelength of this laser light. So we actually do it for use something useful. So now I'm starting with the HL part. All right, so I draw a new diagram. I'm going to draw two new diagrams, to explain this. So I have the screen here. So I take my red marker and for simplistic reasons, I choose this to be the midpoint here. And I look for a point here where I have the first maxima. We can say that this first maxima is about to be here. Here. And this wave here. So I call this point P. And this is, P is a first order maxima, meaning n is equal to 1. Okay, so I have one wave coming out of this slit, one wave coming out of this slit. All right. What is the criteria for having constructive interference at that point? Let's call this source 1. This is source 2. What is the criteria for having constructive interference at a specific point? Frey, you go first.
The difference is a positive integer.
The difference is a positive integer times lambda. What is a positive integer times lambda?
The difference between the distances.
Yeah, difference between the path difference. So if I take the absolute value of the distance from S1 to P, this distance here, minus S2 to P, if that is n times the wavelength of light, I get constructive interference at that point. And if n is equal to 1, it's required here to find S1P to S2P being equal to lambda because n is equal to 1. All right, so my job is to find the path difference. I need to find the path difference between these two lines. Easy if I give you the path difference. Not as easy if I don't give it to you and you have to use trigonometry to do so. Lamia did not agree with the trigonometry part. And it's actually a bit hard to understand because, let's say, this typical distance here, not fixed, but let's say it's in the order of, let's say, 1 meter, right? So let's say that this distance here is 1 meter. And there's a huge problem with this diagram. This diagram is completely messed up. What's wrong with this diagram? Okay, it?
There's no distance between S1 and S2? Does that what you're trying to find?
No, not quite. But look at it. This is 1 meter. What would you typically say that this distance here would be?
Like 0.2?
1/3 of a meter. No, 1/4. 1/4 of a meter.
Very, very, very small.
Yes, but here it is very
Yeah, but
big.
that's because it's a bad drawing.
This is zoomed in version.
Okay, it should be very, very small.
Yeah, it
but
should
it's
be very.
big.
This diagram here is completely out of scale.
Okay, so you can
if I 300 lines per millimeter, that means that if I have 100 lines per millimeter, just to be kind, let's assume that this D is typically around 0.01 millimeter, meaning that this is about 0.00001 meter. This distance here is actually 100,000 times smaller than this distance here. So I'm now trying to draw the diagram in another way, where I now try to draw it in scale. Oh, have faith. I will be able to draw it in scale. All right?
It's already not in scale.
Yeah, it's in scale.
I have little faith in that.
So this line here goes to the point. This line here travels to point P. So 2 point P. Yeah, so if anyone can take this marker and go 100,000 meter in this direction, we can find point P.
Okay, that's
out there. So point P is, far apart. So we draw the next line, and at this angle here, these two lines, they will be approximately parallel. They will be, we can draw them as two parallel lines. This also goes to point P. So even though it doesn't look like it, they are meeting up at point P.
Well, that's a small angle approximation as well then.
Yeah.
Okay.
No. Now I'm trying to draw it in scale. I haven't done the small angle approximation yet. I'm just saying that if I draw this to scale, this is 0.01 millimeter. Then point P then these two lines going from point P, they will be approximately parallel.
Okay.
Yeah. So I have to find, but both those lines are traveling to the same point. Yeah.
How can people make 300 slits per millimeter is my question.
We can do that question another time.
Okay.
One thing at a time. Let's do one. So I have to then find the distance between these two paths. And so this one travel a little bit shorter than this one. Do you agree on that? This one here takes a bit shorter trip than this one here.
But they don't end up the same place.
Yeah, but these two they end up at the same place. This one is slightly steeper than this one. Yeah, point P is. Sure. So that's the only way to draw it. I can't draw a point P here because you have to draw it in scale. But point P is somewhere over here where this kind of meets up at that point.
Okay.
So, in order to find the path difference between these 2 points, we have to draw a line here. I try to rewrite my diagram a little bit. I want to make it a bit steeper. It wasn't too easy to see, so I had to redo it. Make it a bit easier to see.
What is that?
All right. So they're almost parallel, but they're not going to. They're going to the same point. right here, 2 point P.
Now it's really zoomed in though.
Yeah. And this one is a bit shorter than this one. And the path difference can be found if I draw this line here, hitting this one at a 90-degree angle. This little piece here, that is the path difference.
Path difference is S or D?
S2. So this one here, this little small line here, that's S2P minus S1P. That little small piece there is the path difference.
Really?
Yeah.
Oh, it is. Oh.
Yeah, this is more math, so don't blame physics for this. And this angle here, we call that angle here, we call that angle. Guess what we're calling it? Yeah.
Wow.
So crazy. So creative. So creative.
And this distance here, which is the hypotenuse, this distance here, that's D.
Wild.
D.
Okay.
So
Theta.
we have theta and we have D.
So D is here.
Yep.
And then
And
Yeah.
STP.
it's a path difference.
Path difference, yeah.
And then
So that means that the path difference, I just call it path difference. And we're going to use this formula later in quantum physics as well. So we have to have it. And that path difference, if you look at the trigonometry, if I draw the diagram a bit bigger, it's going to look something like this. This is our diagram.
Nice.
Can anyone tell me, using trigonometry, can anyone tell me what is the length of this one?
Yeah, this is straight.
Okay, alright, Anisha?
D sine theta.
Yes. D sine theta.
Yeah.
That is the formula for the path difference. We will use it here. We will use it when we're entering quantum physics world, looking for when electrons interfere.
Nice.
All right.
I'm loving that.
So that's the path difference. So that means that now we know the path difference. Now we can find a new condition for constructive interference. Yeah.
So would it then be 2, n lambda equals d sine theta?
Almost.
Okay.
D sine lambda theta equal to,
The opposite way.
yeah. Yeah, you're right.
Wild.
So that will be the condition for constructive interference. So that's the HL formula for constructive interference. All right. I promised you that I will derive this equation here, so I will do that. Then I just...
We have to
No,
know
I
how
don't
to-
have to draw a second diagram because we can see here that, looking at this diagram here, this theta here is equal to this theta here. If I just draw a line here, if I draw this line here, and I have this theta, so that angle here will be theta as well. I'm leaving it to you, Nishal. Yeah.
Because there was 90 degrees between.
Yeah, so this angle here will be this angle here.
Right.
So this angle here can be calculated. How do we calculate this angle here using S and D? Trig, yep. That's it. How do we calculate that angle here? Hmm?
S over D.
Opposite over hypotenuse.
Yeah, that was tangents.
That was tan. Yo,
Tan theta is equal to S over D.
What do you say?
That's what I that's what I said.
You did.
No, that's what I said.
Yeah, I just backed you up. See that.
Okay, tangent to theta is S over D.
yes, adjacent and.
Adjacent divided by.
Opposite. No, what?
That's great, guys. We're
Yeah.
so good at
It's
this.
near.
How is it
We're
newer?
having a math test about this,
It's
by the way.
S over D. Yeah, that's right. That's right. Correct.
S over D. Opposite over adjacent. All right.
Amazing.
Nonsense.
All right. And then we do this small angle approximation.
Why do we need to do that, by the way?
No, not just doing this. Look at how this formula come from.
Okay.
So
Oh.
for a small angle, sine 2 theta is equal to approximately equal to what?
1. So no, you said this way you told us last time.
I didn't say it was equal to 1. I
Oh,
said no when you said 1.
Me, I said 1. Also.
0.
Oh,
Okay.
boy.
5.
Decent.
Yeah, I thought it was 1. It's almost 1, didn't
People.
Sine 2 when the theta is small,
Theta is.
it's equal to theta.
Oh.
What type of math
What?
is this?
Oh, you've seen that before.
No.
We've never seen it. Anna did not do that yet.
Yeah, we have not
Cut us
said
some
that.
slack. Please explain.
Por favor.
Well, I have done it. We have done small angle approximation before.
You skip me.
All the videos are here. No, we haven't.
All right.
Yeah, everything documented.
No, but in radians, right? Let's just try your calculator. If you enter in radians, use your calculator. If you put sine to 0.01 into your calculator in radian, do that.
0.01.
Everyone is doing it.
It's in the simple harmonic question.
Yes.
One of the simple harmonic.
It was in the simple harmonic motion. Manju kind of saved me there.
The Manju.
It's not the same.
It is the same.
No, it's
not.
not.
It's not the same.
Yeah,
No.
it's almost the same.
Yeah.
And if you do it in
No,
It's not the
radians,
same.
It's not even close.
Whoa. Why don't you speak louder?
It's not the
the
same.
theta is,
Sound
I
close.
think, less
Hmm?
than.
Oh,
even close.
maybe I have radiance
It's
on.
not
I haven't
even
checked.
close.
It doesn't.
If you round it up by 5.
Have you set your calculator to radians?
Yes, it's not even. No, but it's, if you round
No,
it up,
mine
it's
is
the
in
same, but
degrees.
we don't-
Mine is in degrees. It's the same.
Yeah, no, but you
Mine
don't
is
round
in
it up.
degrees.
So
Mine
it's
is in
not the
degrees.
same.
It's not the same.
In my opinion,
what?
it's
No,
not
but
the
what's
same.
the explanation for it? It's just
Lines go on fertility. You kind of assume.
It's not really an explanation. It's just that we see that it's true. For very, very small angles, you basically get the same thing.
Draw unit circle.
Yeah. And I'm going to draw the unit circle.
You're not.
And if I do tangent, you get the same thing. It just doesn't work for cosine. Stop asking me math questions.
Cosine is the isn't it the height?
Focus on the important thing. Ask Anna if you want to have an explanation to that.
Cosine's the
Oh,
height.
how-
Yeah,
Small angle
yeah. If it's less than 10 degrees,
Yeah, but
you can use small angle approximation, but you have to convert it to radians to make it work.
Okay.
Yeah.
And you know that it's going to be less than 10 degrees.
Yeah, we assume so now.
Uh,
Look at this. If we did remember when we did the experiment on the whiteboard, those fringes were very close apart.
oh, what?
Yep.
Could we have more tests, but that don't really count? Like the grades don't count, so that we can like get used to tests, and
Please, Pablo.
that would be great, actually.
let's focus on the matter at hand, all right?
Oh.
You can break.
Okay, in the break. Okay.
All right. So that means that if the angle is small, which would be true for focus.
So theta equals this.
Yeah, so that means we have two forms. So that means that theta, this first one here, tangent to theta would be then equal, so that would S over D would be reduced to theta S over D using the small angle approximation, and D sine theta would be reduced to, and let's say we assume that n is equal to 1. That would then simplify to lambdas. That would be lambda. So that would d to theta would be equal to lambda. So if you combine those two equations,
Oh,
this
the
one
d
here,
sine theta n equals n. What?
Theta
Oh.
lambda.
What happened with the d sine theta?
yeah, what happened to d sine theta?
Basically, sine theta is equals to theta, and
Yeah.
so we don't care.
Yeah.
Is it the same for tan and cosine as well?
No, only for tan.
Only for
Not cosine.
No.
Okay.
Yes, exactly.
Yeah, but that has to do that. But that has to do with the definition of how you've been calculated.
Sure.
So that we combine these two equations, you will then get
D of s big D.
d over s over d
Big D of d d.
is equal to lambda, which would then become s
Oh.
equal to lambda over d.
Yeah.
Yeah.
Yeah. That.
All right. So that is how we derive this equation for Young's double slit experiment. But that